Righto. So yeah, got that submission portal sorted. So yeah, tonight we're going to go through the energy analysis for the final project. So as well as producing the report, there's the energy analysis to go through and include that as an appendix to your report. So I haven't produced a pro forma for this report. So you've had the pro forma for your first two reports to work with. That gives you a bit of an idea of how things can be structured potentially. Feel free to use that same sort of structure for your third report. However, you've got a bit more autonomy about what you choose to research and advise in regards to those materials. But what you will have to do is this. Now, this is, I guess, it's a larger part of the assignment, but it's the sort of thing that we should be able to easily complete this evening within the class, if you wish. So we'll go through it first, but I suggest having that spreadsheet up in front of you as well on your computer, so you can put some elements into that as we go through it tonight, and work through some things. And also, I'll be putting this recording onto the Learn site as well for you to go over again at home for completing the energy analysis. So to start on that, so we'll be looking at electrical energy, lighting, air conditioning, computers, and refrigerators. So all aspects which are fairly important to the use and the running of a commercial building. So you have this this Word document here for the energy calculation information, and that relates to the building that we're using for Project 3. So I suggest it's a good idea to have that spreadsheet up, have access to the plans for the building, and then have this Word document here as well. So electrical energy is used in watts, and that should not be new to anybody in the room. Everybody's comfortable with that, and you've looked at what ratings of appliances previously, or watts on globes, things like that. Has everybody had a look at that? Don't know if I'll just sneak over your computer here, Christian, see if we've got wattage there. So an annual consumption of 109 kilowatt hours per annum. That's in Spanish, año, but we don't have a. Do we have an English translation on this one? No. We've got So we've got an annual use of electricity for this computer. Now, obviously, so for computers, it's going to be an estimate, because let's say we're using that computer for gaming. We're using the hard, using a lot of processing power. That computer is going to be burning through more energy than somebody just on Facebook or something like that. So you've got your various different uses of that very same computer that will cause different usages of that. And also, like refrigerators, they're often expressed in kilowatts per annum as well. But that being said, there are some more efficient types of computers, or more energy-hungry forms of computing as well. I think, Tommy, if we were to have a look on the back of your laptop there, it might. Well, actually, I've got a laptop here. I might have wattage on this one. No. So we've got amperage. So we've got amperage supply, but no wattage shown on the back of this one. Wattage usage. However, on the bulk of electrical equipment, there will be some information about the wattage that's used. Although it's expressed in watts, typically we're dealing with kilowatts, so thousands of watts. So 1,000 watts equals 1 kilowatt, and if we're using 1,000 watts for an hour, that's 1 kilowatt hour. and that's the unit that we get charged in for our electricity bills. We pay like 38 cents or so per kilowatt hour. So let's say I've got a bar heater at home, winter time. It says the wattage on that is 1,500 watts. I'm using it for 3 hours. Can anybody tell me how many kilowatt hours I would have to pay for? Yeah, 4.5 kilowatt hours. So it's simple as that. With lighting, it used to be that, well, certainly myself, I'm a bit more of a dinosaur. You would go into shops and you go, all right, I think in this room we're going to need an 80 watt or 75 watt globe. This room we're going to need a 100 watt globe. Here we're going to need a 40 watt globe or 25 watt globe, etc. And you choose an incandescent globe, and you make your decisions based on the wattage from what you understand as how bright they are. That has certainly been shaken up significantly by new technology in lighting and more efficient lighting coming onto the market, and you've got things like LED globes that put out a lot of light for very low wattage. And so now at the supermarket, when you're deciding what sort of lights you want to buy, you've got to look at things like warm light, cool light, what sort of lumens it's putting out, what's the price tag, how many sort of lumens am I getting for the price, and compare that with wattage. So there's many more. So it's become more complicated. So as we can see in this table here, for the old incandescent light globes, your 40 watt would put out 450 lumens, 60 watt 800 lumens, 75 watt 1100 lumens, and 100 watt about 1600 lumens. Contrast that. So there's all sorts of technologies in lighting coming out now. Apart from this halogen incandescent, there's another form of lighting as well. I'm not sure what that one's called, but I've got some of those globes myself at home, and yeah, they've lasted well. It's a fairly nice warm light. But anyhow, so let's say it's our compact fluorescence. To produce that 450 lumens, they only require 10 watts. And to produce that 1600 lumens, they only require 20 watts. This is on average. So you've got different quality compact fluorescents and different energy ratings of them. But then for LEDs, so your light emitting diodes, they're that one step more efficient once again. And yeah, and so with 19 watts, you can produce 1600 lumens. So that's a lot of light for very low wattage, very low power consumption. And so it's not just in, well, in fact, I guess in terms of lighting, for lighting in buildings, LEDs has been taken up slightly more slower than in other forms such as automotive and signage and things like that. LEDs are getting used quite broadly in automotive applications now as well, because of the low wattages required and the brightnesses. So when we think about lighting in an office, it's not just a matter of going, oh, I think we need about this much light, and we produce that. It is actually governed by an Australian standard that is referenced within the NCC, and that's Australian Standard 1680. As I mentioned earlier, the process that we go through in tonight's lecture, or in this task 3, is a very simplified process, and it's just in looking at lighting from above, so task lighting, so it's the lighting that comes down and illuminates our area for working. But if we were to do a lighting design for a building, we often think about much more than just task lighting. We think about atmospheric lighting, about lighting certain walls, about creating delineation of spaces through lighting, and also illuminating areas that, like, let's say we had a hallway to illuminate the end of a hallway to invite occupants down through that hallway is also an important thing. So there are many aspects to lighting, but what we're looking at in this is just simply task lighting. Beyond those things, think about colour temperature of light, warm and cool. Can anybody explain to me what that may mean in terms of colour spectrums and so on? Warm light and cool light probably should be fairly self-explanatory. There. What does a compact fluorescent, well, like one of these fluorescent globes put out? Is it warm or cool? Yeah. Yeah. And your old incandescent light globes? Yeah, warm light. So it's about that spectrum of light. And they have essentially different functions. So within house lighting, typically you want a warmer light than the bright than the cool light. But cool light can work fairly well for task lighting, where you need to see a lot of contrast and detail. We also have to think about colour contrast and reflectance of desktops. So how much light is then given off, and other surfaces such as walls and ceilings. What the reflectance or reluctance of those other surfaces is going to be. Have to think about glare. So glare is in the main unattractive because it can be tiring on the eyes. We have to think about the distance between globe and the surface that it's illuminating. Light is diffused and it's also lost throughout distance. If I grab one of those, those giant halogen lights that are out there in the foyer, put one here like this is going to be super bright. I'll probably do some damage to my eyes by doing that. But set 12, 13 meters up in the air and putting light out, they're fine. They can illuminate a large area. So we have to think about that height from the work surface as well. And then also think about the tasks being performed. If I'm going to be a jeweler, if I'm setting diamonds into fine jewellery, I'll want a lot of light, and I'll want that light to be well focused on the work that I'm doing. But if I'm, for example, reading or something like that, I'll need a far lower light for doing that. And if I was to be reading a book constantly under really intense light, that'd be fairly tiring on the eyes. So the Australian Standard 1680.1 sets out a table for the lighting requirements for various different areas. So movement and orientation. So interior is rarely visited with visual tasks limited to movement and orientation. So let's say a fire isolated stairway, for example, corridors, cable, tunnels, indoor storage tanks, walkways, these type of things where we're moving from one place to another. Rough intermittent, so staff change rooms, live storage of bulky materials, dead storage of materials needing care, locker rooms, etc. Waiting rooms, so illuminance of 160 lux. So this column here represents the lux required. So for our corridors, etc., only 40 lux required. Change rooms, 80 lux required. For waiting rooms, general fabrication of structural steel, casting concrete, etc., 160 lux. For school rooms, so in here, 240 lux, which is probably what we're at for this. And then routine office tasks, reading, writing, typing, inquiry desks, 320 lux. Inspection of medium work, fine woodwork, 400 lux, etc., etc., and it goes on. So the example that we'll be working through tonight for our equation for working out the lumens required in a certain room is going to be based on this 240 lux. So this room in here. So we're working out how many lights we would need, or how many lumens we would need for this room to illuminate the areas, to illuminate our work surfaces that we're working on. So we need to provide illumination of 240 lux. So that 240, that comes from this table here. So ordinary or moderately easy, school chalkboard and charts, etc. So we've got to get 240 lux. And let's say this room is 250 square metres. Now this room is much smaller than 250 square metres, so let's knock out some walls, expand that out. So we've got 250 square metres of a classroom that we're going to be lighting up. Now the calculation gets a little bit more complex when, well, we want to determine what our lux are, we want to determine our luminance per lamp, but we also have to consider our coefficient of utilisation. So that coefficient of utilisation, that relates to the light which is brought back and received by the eyes. So we're working in this position here. There's going to be a coefficient of utilisation for this particular task for doing this. We also have to think about the light loss factor. So let's take a standard height of 2900 from the work surface, and then, well, actually no, it's going to be 2 meters from the work surface, a 2900 high ceiling, 900 high table, 2 meters, and we get a light loss factor as that light travels through the air. Those figures are going to be basically the same for whatever scenario you're doing a rough calculation of. Now, if you're a lighting designer, you would pull these apart and you go, okay, our coefficient of utilisation for these particular tasks is going to be this. Our light loss factor is going to be this. You'll go far more into that. This is just a very simple calculation, and so you can use this coefficient of utilisation and light loss factor for other just general calculations you wish to do in regards to lighting. So if we take this, our illumination equals our luminance per lamp multiplied by our coefficient of utilisation multiplied by our light loss factor and divided by A, our area per lamp. So we're treating this calculation as if we're just lighting up that whole area with one lamp. How many lumens do we need to get out of that lamp to do this area? So if we put in, we want to achieve 240 lux. We got that from our table. We don't know what our luminance per lamp is. That's what we're trying to work out. So we've got that in there, multiplied by our coefficient of utilisation and our light loss factor, divided by 250 square metres. If we extrapolate that equation to isolate our luminance per lamp, then we have the equation of 250 square metres by 240 lux divided by 0.48. Can anybody tell me where we get 0.48 from? Yeah, that's cool. So
6 times 8.
Yeah, exactly. 0.6 by 0.8.
Because you need to take out the L, you put that as a quotient.
Yeah, yeah, exactly. So to isolate L, then it has to be this amount divided by that, because that by this amount equals this divided by that. That's our okay, so that's algebra. So our 0.48, that is 0.6 times 0.8. Now in your assignments, in your work, you're going to use exactly those same figures. Our coefficient of utilisation won't change. Our light loss factor won't change from this scenario. So what will change is your square meterage. So you're going to have different square meterage, and you're also going to have different lux as well, different lux requirements. Heading up to this table, can anybody tell me what sort of lux requirements we'd want for our office block? Yeah, 320. So we'll be looking at that. So we're going to be something more like 700 square meters by 320 divided by 0.48 gives us our required lumens. But for the purposes of this, we can do 250 square meters multiplied by 240 lux divided by 0.48 means that we need 125,000 lumens. So that's just for 250 square meters, so for level 1. So if there are 30 light fittings, you would need 4,340 lumens each light. Now that's a little bit backwards, because what we need to do is go, okay, we've got 125,000 lumens to achieve for this room. That's how much light we have to provide for these square meters. What sort of lighting situation do we want? What sort of yeah, we'll probably want LEDs. So we can have a look and say, okay, what LED office lighting scenarios are there? And can anybody suggest to me what sort of things you'd be, if you're going to be searching for this on the internet, what would you be putting into that search to find the LED office lighting? I'd probably put in LED office lighting myself. And then be looking for things that'll fit within like a ceiling grid system. So we've got, actually, no, these ones are still fluorescent tubes in here, but you can get LEDs that are in a bay, like this, that are hung. That might be your choice. Or you might go for, if you're going to have a ceiling grid system, or you're thinking that's the way to go, find LED light bays that fit into those 600 by 600 grids. I know they exist. So small 600 by 600 light bays that go in. So there'll be a plethora of options around that. Just choose one and go, these are the lights that I want to specify for in my building. They're energy efficient and they're readily available. There's a supplier for them in Adelaide, for example. So, or they're from a good quality manufacturer. So look for these things and go, okay, these are the lights I want to do. How many lumens does each bay put out? And then let's say each bay puts out 5,000 lumens. Then we go, okay, 125,000 divided by 5,000, what's that? It's 25. So we'll need 25 light bays. Have a look at our plan and go, oh yes, we can fit 25 light bays in there. Great. That's what we're going to go with. And so then we'll, actually I might want to bring us back to here and get the energy calculator open as well. So go through this process and record all of that. Record all of those notes, because you're going to be making some recommendations to your client based on that. So what sort of things will we be putting in our report and recommending to our client based on that, do you think?
Energy efficiency, the cost.
Yeah. So I think well, yeah, definitely, yeah. So talk about the the energy efficiency of it, and that will express itself in the Excel spreadsheet as well. So those figures will talk for themselves, and talk about, okay, this is the style, this is the way they're mounted, etc. So this is why I've chosen this product. But then also talk about, we have to achieve these amount of lumens, right? Because your client might go like, oh, well, how much lighting do we need? Does this person actually know what they're talking about? If you go, yes, we've done these calculations, these are the lumens that are required for that space. This is why we've specified this. Now, with our Excel spreadsheet, we've got the option of, so we've got, oh yes, yep, no, that's fine, because I thought there'd been some mucking around happening on this as well. But we've got our option here for 60 watt fluorescent globes. So knowing the lumens, so we've calculated the lumens required for our office. So let's say it's that 125,000. We're doing that in this example. Going back to this, we can go, all right, 125,000 lumens with a 60-watt incandescent globe, and I'll have to get my phone out to do that calculation, unless anybody else has got their phone handy there. Oh, I thought you were going to do the calculation for me. So 125,000 lumens divided by 800. How many globes are we going to need for that? 15.62, so we're going to need 16 of those globes. So in our spreadsheet here, put in 16. That's for the example that we're working at. This is not for your calculations yourself in your project. That's based on our classroom of 250 square meters. So yeah, that's 16 or 17 light globes in there. And then what's the watt rating of our 60-watt fluorescent globes? 60 watts, exactly. Yeah. Sorry, I asked you dumb questions just to make sure you're still awake. So wherever we have one of these yellow squares, that's where we can input information. So in this right now, I'd be going, and was it 16 or 17 we needed for that? 16, wasn't it? 16. So 16, and then at 60 watts, that's going to cost us $660 a year to light that room. Now, our low watt LED. Well, let's quickly find a low watt LED. Or has anybody found one yet for office lighting? Osram?
Yeah.
Oh, Osram. This room. So,
High efficiency, 140 lumens.
140 lumens for how many watts?
Didn't say.
Okay, let's look for something with a bit more information with it.
Indoor light management.
Possibly. Or indoor luminaires. For suspended mounting, for sure. Oh, that's what you're looking at before, isn't it? Let's have a look at Terrace Square. All right, might have to put a little bit more in the search to get this happening quickly, because they may have all their product information here, but it's not jumping out at us quickly. You got something?
This is different company.
Yep.
Looms, kilowatts, maximum power,
21 watts.
90 looms.
Yep. Is it? Oh yes. Oh, that's 90 lumens per watt. So that's going to be 21 watts by 90. So 21 by 90 equals 1,890 lumens per 21 watts. So we've got 125,000 divided by 1890 equals so that means we need 64 of those light fittings at 21 watts. So 21, and we'll need 64 of them. Well, that's not really stacking up, is it? Right, have to do a bit more digging around for some of those figures. So we'll find some light fittings, and then some efficient light fittings. Work out how many you need by how many lumens they produce per lamp, and then how many watts, and put that in here. So that's for the lighting. Then the next thing is for the air conditioning, and as I mentioned before, air conditioning systems to calculate energy, well, the requirements for air conditioning systems is really quite complex. So you've got things like the number of occupants, the climate of the building, location, the building fabric, walls, roof, floor, insulation, ceiling height. Even got like the colour of the building is going to make a difference. Orientation of glazing is going to make a difference. Times at which the building is used is going to make a difference as well. So frequency of occupancy, etc. So we're not going to go through all of that. I wouldn't understand half of that myself. What we are going to go through though is to do a simplified analysis of that. So a very general guide is approximately 140 watts per square metre for the conditioned space. So we look at our 250 square metre classroom. We're going to have 140 watts per square metre. So 250 by 140 equals 35,000 watts. So 35 kilowatts to cool, to air condition a 250 square metre space. Well, now actually we'll wind that back a bit. So our cooling power is going to have to be 35,000 watts, because cooling and heating power is measured in watts. Now the old systems used 1 kilowatt of energy to produce 1 kilowatt of heating or cooling power. Typically, now that's just very much rule of thumb, massive generalization there, but we'll treat it as such. But more efficient modern systems can produce that 140 watts of cooling or heating for a third of the input energy. So they require much less energy input to produce that. So let's say we require 35 kilowatts of heating. So our 35,000 watts for 140 by 250 square meters. An inefficient system will use the same amount of input energy, so 35 kilowatts to run that. So we run that for an hour, we have to pay for 35 kilowatt hours. Run it for 8 hours, we have to pay 8 by 35 kilowatt hours. So quite expensive to run. Whereas an efficient system will use around 11.6 kilowatts to run it. So 11.6 kilowatt hours for our first hour. So if we then refer back to our spreadsheet, those figures are given to you. So the watt rating of our inefficient air conditioning system is 140 because we need 140 watts per square meter to run that. It's got to be running for 8 hours a day, 5 days a week, 52 weeks of the year. Now that is a very simple approximation of that. We're not going to be running at maximum capacity every day that the office is open all year. Summertime it's going to be running flat out. Wintertime it's going to be the reverse. Well, it's going to be heating. Spring and autumn it may be doing very little work at all. So this is not particularly nuanced at all. But if we skip that hurdle, or we get over that, can anybody tell me what figures we'd be putting in here for our quantity? Given that we've got a watt rating of appliance per square meter of the building. So
where was that again?
So in the Excel spreadsheet for the air conditioning. So if we go back to here, so
Down.
yeah. So very general guide is 140 watts per square meter. So our inefficient systems are 1:1, with the input required is the output in cooling power produced. So in the spreadsheet there, what we'd be looking to put in that spreadsheet is the square meterage of air conditioned space. Because we've got 140 watts of cooling power per square meter, therefore we'd put in, this is for our 250 square meter classroom, 250 in here. So 250 square meters by 140 watts per square meter, 8 hours a day, 5 days a week. It's going to cost us $24,000 a year to run. That's Now that's a fairly inefficient system. Run for 8 hours a day, 5 days a week. So realistically, typically we're not going to be spending $25,000 a year to air condition 250 square meters of office space. So it has to be seen as that. But certainly with the costs of running commercial buildings, they are also very high. And we are dealing with very large numbers here as well. So be aware of that. When you go putting in, let's say, 700 square meters for your combined 3 floors for your air conditioned space, that's going to be a fairly scary figure. $67,000 a year for air conditioning that. Now, if we put that same in here, so 700 for that, for example, so our running it efficiently knocks it back to 16. If we deal with our 250 square meters for our example, 250, so dealing per square meter, the expensive old energy intensive way of cooling is 24,000. Energy efficient method of cooling is around that 6,000 per year. And that's probably a bit more what we would expect. Now, if we've got a 250 square meter house, certainly we don't want to go spending $6,000 a year on air conditioning, but we're not going to be air conditioning it for 8 hours a day, 5 days a week. And it's not going to be, probably for 3/4 of the year, it's not going to be air conditioned. It's going to be air conditioned through those summer months, and to varying degrees. Yeah, I don't actually have air conditioning in our house. So our energy bills are high during winter time, and in summertime it's fine. But I think for most people it's the inverse, isn't it? Anybody here have air conditioning systems in their house, refrigerated or so? Is that the case with your place, that winter time there's not a great deal, not very high bills, and then summertime it's quite high? Yeah. So that's sort of what we'd expect, that you'd be ploughing a lot of energy into air conditioning during the summertime, but then the rest of the year you're not. So for computers, let's go back to here. So that's air conditioning. Does everybody understand that to the extent that that's sort of roughly applicable? And we'll be able to complete the spreadsheet and also use that. So power consumption by computers can vary greatly depending on many factors, depending on the graphics use, if power save modes are enabled, etc. One of the biggest savings can be made if workers shut down or hibernate their computers before leaving work so they don't consume power when not in use. That's great. That's occupant behaviour. We can model occupant behaviour as well. If we were to get quite complex about this, we're not going to get complex about this. In our spreadsheet, we're going to be looking at, all right, computers are going to be used for 8 hours a day, 5 days a week, 52 weeks of the year. They're going to be running the processors just sort of, general use. They're not going to be gaming. They're not going to be playing solitaire. They're going to be doing something in between. So we've got 90 computers, and 90 computers have been put into both. So that's for our 3-story office building. That's probably fairly reflective of the number of computers we're going to have in there. Now we've got an average watt rating of that computer at 250. Actually, I guess let's not do the Google search thing for watt rating of computers, because that gets a little bit more difficult to find even than lighting, and we don't want to spend a lot of time mucking around with those searches in the class. Well, yeah, but that's not a particularly efficient way. So we've got these desktop computers, which is great for processing. If we're going to be doing renders on 3D images and things like that, that's excellent. But a way to use far less power is to use things like tablets and laptops. Like I've got a Surface Pro. I don't remember what the wattage on that is, but it's something like 19 or something. It's something ridiculously low. You can still run AutoCAD on that, AutoCAD 2D, doing, yeah.
It's pretty slow though.
Yeah,
mine struggles.
Okay, all right, yeah. Mine's not too bad actually. I don't, yeah. Yeah, but maybe I'm fairly slow and what I don't demand it. But I'm not doing any 3D on it. So that's just AutoCAD Lite 2D for documentation. So you can, but what I was wanting to say is there are actually computing systems that have very low wattage requirements. So your laptops and your tablets and things like that are actually fairly adaptable for a lot of office situations. For much of the work that you do in offices, you can actually use those low watt examples. So let's say we're going to be using an efficient laptop or a tablet or something. We'll put in 19 watts there. So our 90 computers at 250 watts, it's going to cost 15,444 per annum. But if we use laptops instead, then it's going to be that 19. If you want to get a little bit more technical and go, okay, but with a laptop, I'll probably want an external monitor. Let's add an extra 30 watts to that. Go to 49 watts, for example. Yeah, it significantly increases our power usage, and by all means, you can be complex with that if you wish. Just stipulate that in your report. Say the computer system we've chosen is this laptop with a docking station or something, an external monitor or two, to explain your wattage use there, because that's going to be different for every person. Well, all of these things are going to be different for every person. It depends on the lighting system that you choose for that, and for your computing systems, etc. So while we're here, let's go. I'll just put some figures in here. We need 14 of these at 16 watts, for example, for our LEDs, just to get some figures in there. Now we've got, well, we'll go back to here as refrigerators, and then I've got amenities like down there. Okay, we'll get into refrigerators first. So probably, as you would all know, refrigerators have become far more energy efficient now as well. Well, there's certainly far more energy efficient than the old beer fridge or so that you might have out in the garage. That use a lot of energy, by the way, and probably aren't really worth running to cool beer. But you can save yourself a lot of money by upgrading your refrigerator to an energy efficient model. For doing that comparison, further on down here, there's the energy rating calculator. I'll just copy that and paste it into here, so we're not opening from that link. So with this online energy rating calculator, you can compare a whole lot of different products and go, okay, well, this one has these particular features, this size, etc., and it's going to be using this amount of energy. So here we go. So factors which affect power consumption include the quality of the insulation materials used, the seals, the compressors, and other components. Because refrigerators are on all day, every day, the annual energy consumption of the product is expressed as kilowatt hours per annum. Refrigerators are compared by their size, measured in litres. Similar size units should be compared unless the decision to choose a smaller fridge is possible. Further on down here, you're asked what is the best approximately 500 litre no freezer refrigerator? How many stars and what energy use? And what is the energy use each year? So the way we go to calculate that, so obviously click on fridges. We're in here, we click on fridges. Now, do our search based on, and how do you want to search? Any suggestions there? Do we search by model, by all models, energy star rating, energy consumption? Yeah. Well, I'll go. The way to go, I think, is all models, because that enables us to compare. So if we choose all models, if we go, oh look, I want to buy an LG, and I don't care about Westinghouse or Fisher & Paykel or Kelvinator or whatever, right? Then we're not really making that comparison, and we might be missing out on a really good refrigerator for that. So let's get all models up here. But the type of fridge, we want fridge only. We don't want a freezer in this one. So fridge only, and then select. Oh, our configuration is going to be fridge only. We'll leave that one blank. Now we were asked to find one around that 500 litres. So our capacity, we can use that sliding bar. And bring it to that range. And then we don't care about what brands. Go apply filter. And that'll tell us, okay, we've got this one here, capacity 498, and it's all been ordered in star ratings. So we can have this 3.5 star Fisher & Paykel 500 litre or 498 litre fridge. So is that going to enable us to? What's that?
Doesn't do it. Yeah.
Doesn't let you select it. So within our Excel spreadsheet, yeah, we're going to have to find the wattage of that. So I'm going to copy that. Yeah. Anyhow, so we can go through, do some searching on that model. We won't won't pour through that today. Yeah. So unfortunately, yeah, it's not letting us select those, but we can find out which model we want to go with for that. Like, yeah, actually maybe serve us to pour through this the options there for finding information about those particular models on this site. But yeah, we've selected our fridge. We'll have to find out those kilowatt hours per annum. Also, in regards to solar panels, photovoltaic panels, so that's something that I say there's a lot of industrial solar panel setups going on now with the cost of power, and because power usage for offices is typically during the day, it's certainly hit that price point now that it makes a lot of financial sense for major developments to be putting on solar panel systems. This place here is no exception. So I'm not sure if it still is, but this was the largest non-residential solar setup on this building here when it was installed. But yeah, I've got a friend who installs industrial solar systems. I haven't caught up with him for quite a while because he's absolutely flat out, and he's away just about all the time. So that'd be very interesting to get a bit of an understanding about that. But from what I understand is there's a lot going on, and that sort of feeds back into our cost of power as well, because if major power users are going to be going to solar, it doesn't diminish the network requirements for that, but it diminishes some of the profits for retailers in that regard. So there's that feedback loop there. Anyhow, so there's a lot going on now with solar panels and commercial properties, and a lot going in. But with solar setups, it's not just as simple as, okay, we buy a 1 kilowatt system, that 1 kilowatt system produces 1 kilowatt hour every hour, and then sun shining for however many hours in the day. That's how many kilowatts our system produces. We don't get perfect efficiency from our systems. So it depends on the location as well, the location within Australia. Because if let's say you're at Alice Springs where not many clouds are flying over top, you're going to get higher efficiency out of your solar panel system than you are in Adelaide, for example, or in Hobart, where there's quite a few clouds flying over the sky. You're going to get a fairly inefficient return on, or a less efficient return on your solar system. And so this chart indicates Adelaide's solar panel system with a capacity of 1 kilowatt will on average generate 4 kilowatt hours per day. So this is daily production, average daily production. Our 1 kilowatt system is going to produce about 4 kilowatt hours per day. Generate more in summer and less in winter. So one panel can generally generate around 200 watts, which equates to 0.8 kilowatt hours a day in Adelaide. Does that make sense? So 200 watts by our 4 kilowatt hours. So for 1 kilowatt system, so divide that by 5, multiply by 4, we get 0.8 kilowatt hours per day in Adelaide per panel.
Do we have to write about that in the assignment?
No, you don't have to write about that in the assignment, but what you do have to do is work out how many solar panels you can get onto the roof.
All right.
So you go, all right, this is how many solar panels we can fit on this roof. They're going to be, they're 200 watts per panel. If we refer back to this, each panel is going to produce 0.8 kilowatt hours per day. So let's say we can get 300 panels onto that roof. So 300 by 0.8, maybe people do that in their heads. I'll have to use my phone by 0.8. So 240 kilowatt hours per day. Within our spreadsheet, we're given our energy use and how much energy is saved. Okay, that's interesting. This has got inputs at 300 watts per day. I might actually, well, I'll leave that as it is. So we have to, first of all, we have to calculate how many solar panels we will need to cover our energy use.
And wouldn't you need to know how much they cost as well? Because
yep.
it says down the bottom, how many years will it take for the solar panels to pay for themselves?
Yeah. I think so. That cost of panels, so $400 per panel. So that's in there. So just working through that. So the first calculation below is to determine the energy kilowatt hours generated by one panel per year. The second one will divide the annual energy use by the solar power generated. So just pause that. What's that? Yeah.
Making sure.
Yeah. Thank you. So that's our grid versus standalone. And yeah, sorry for those at home that missed that little bit there. For our energy analysis, for determining how many years it takes to pay the solar panels off, we've got the cost of the panels divided by our cost of electricity per year. So divide 26,301 by 9,478. That gives us how many years it would take to pay the panels off. And you're going to get basically the same answer from the energy intensive scenario. And that's because it's making the same assumptions about we're using all that power while we're producing it, which is yeah, as I said before, an oversimplification of that. So now we've calculated that. So to do that, we've plugged some numbers in here. We can take those numbers. Well, let's leave this one out. Our refrigerator, our 3-star refrigerator, 408 watts rating of the appliance, and then that's kilowatt hours, 816 kilowatt hours per year. So that's right. So we're going to then work out. So we've gone through. We've worked out our lighting for the office. And then we also have to work out what our amenities lighting is. So within your spreadsheet, you're asked to provide 21 lights for amenities lighting. Now previously that's a 100-watt incandescent globe. That's not a yellow square, so that's locked in there. But what you're asked to do is find a globe that's a low watt LED or some low watt globe to produce similar sort of lumens to that 100-watt globe. So having a look back at our table up here, got our 100-watt globe that was producing 1600 lumens. We can get a 19-watt LED to produce 1600 lumens. So just for the purposes of this, we'll put in 19 watts there. But do your own research. This asks you to find out what globes and specify those globes for the customer, because that table is also a couple of years old as well. Back there, you're going to find even more efficient bayonet or screw fit light globes. So choose a light fitting to provide at least 1400 lumens. Note the model number and type at the end of the report. There'll be 21 lights for amenities. Then finally, the last thing to do with the energy calculation portion is to work out how many photovoltaic panels you can get onto the roof. So that's what you wanted to find out. So the average panel size is 750 by 1500. That's a fairly standard panel size. So like anything, we're talking about those increments of either 150 millimeters or 300 millimeters. So 5 lots of 300 millimeters, so 1500, and then our panels are half that in the other direction. That enables you to lay panels out in all sorts of fashions and still produce a fairly neat grid. The way that panels are installed on roofs, and this is slightly misleading how there's a gap between panels like that. So that's from the Revit library. You get panels. When you install panels, you butt them right up next to each other. You install them, or typically install them as a bank. But when you install them on aluminium rails, you have you've got your, let's say you're doing the installation on a corrugated iron roof. No, it's pretty dry, that one. Okay. This is our custom orb sheeting here, like that. You have an L bracket, and you fix that with a roofing screw back down into your pillar. So you pop, if it's a roof that already has roofing screws, pop that roofing screw out, put your L bracket on, fix your roofing screw back down. That's for custom orb sheeting. For tiles, it's really annoying because you've got to grind out a piece of the tile, flip it under there, and fix it to your tile button underneath. But that's how it's done with custom orb. That's fairly simple. And then you've got these fixings here that lock in to an aluminium rail like that. And then your panels go on top of that, and they've got a locking mechanism that locks them into those rails. So you set the rails out, and then you drop your panels in and lock them in to those rails. That's fairly simple. But then you've got wires underneath your panels. You've got to bundle up, pick up your wires, use cable ties, and then you join all those wires together. So you have your panels tilted up, you join them up together and drop them down. For doing that, you need to have space at the end of your panels for when you're working. So that installation, yes, you can install a bank of panels and then another bank of panels like that. But if there's a problem with any of those panels later on, and you've got a bank that's 5 panels deep and you've got to get to one of them in there, that means you have to take off a whole series of panels to get to that one that's further in. Does that make sense to everybody? Whereas when we've got them together like this and that 600mm between them, you can then go down in between them, undo that panel from the rail, lift it up, do your servicing on it, etc. Or pull it out and replace it. So for your solar setup for on your roof, for doing your banks, leave a 600mm gap around to ensure that you can access all of your panels. So with that on our roof, and I'll just draw it here. Sorry for the folks at home that can't see that, but what I'm doing is I'm just drawing some banks with panels, and they can be all set like that. We need to have 600 millimeters to our edge, and then 600 millimeter gap between our next bank, like that, with a 600mm gap at the end, etc. Is that fairly straightforward? Now, I think, yeah. I'm fairly sure we don't actually have the Revit model for this building on the Learn site. So although the panels that 1500 by 750 is available in the Revit library, it's something you're going to have to do manually. So work out the roof space, draw that up. You can draw it up in Revit if you wish, or in AutoCAD, and just quickly draw yourself a solar panel that's 750 by 1500, and then do your layout. So you can do your layout in a CAD program, or if you're unfamiliar with CAD, so some people are doing this subject before they do any other CAD subjects, you can do that all by hand drawing as well. It's fairly quick and simple to do as well. You can draw it up and just calculate, okay, this is how many panels wide I need. So the width of the building minus 1200 millimeters, so 600 millimeters either side, I can produce a bank this long, etc. So muck around with that and determine some panel layouts and see how many panels you can get on there. Is that going to be fairly simple for everybody with that explained in that fashion? So what approaches will people personally take for this? Is anybody going to quickly draw it up in Revit or AutoCAD? Do you think?
Might do it on AutoCAD.
Yeah.
Paste it.
Yep, for sure. And then print it to PDF or so. I mean, just chuck it in the report.
Just
Jayan?
Yeah, 250 square meter, and then work out 750 by 1500, just a little square, and then just line up everywhere. Then 600 mil gap.
Yes, 600 mil gap.
How many I can put into the?
Yes. So how many panels can you fit on the roof?
Yep.
And so you're going to be doing them in banks of 2. So like you've got here in this diagram, you're going to be butting them up together like that. Except you're also going to butt them up neatly side by side. You won't have a gap in there. And so those banks that'll be 2 wide, set those out on the roof. But you might arrange a whole lot in this fashion, but then you might arrange some in a different way as well, because you can do that, and you can even do that with that gets a bit complex for the installers because they're running rails this way and then they're running some rails this way. But yeah, let them do that. It's about how many panels you can fit on the roof. Is that yes? So you just have to enable 600 millimeters around the outside of every bank that you do. Yeah, I guess. Yeah, no, we'll just leave it at that.
For each bank of 2, you mean? Like that.
Yes. So when you've got when you've got them paired like that, So our banks will have 2 panels, or be 2 panels wide. Right, and that pretty much sums up all that's required for that final bit, that final report. Any questions? from anyone in that regard?
With the cladding,
Yeah.
how intense does the FRLs, do we need to go into the fire resistant properties of it?
Well, you should be able to specify what those FRLs should be, because we don't know what situation this building is going to be in. So we have to assume that it's going to be on a boundary, that it's going to be close to a fire source feature, because
I'm doing curtain wall as a cladding feature.
Yeah.
Is that okay? Or
Yeah, that's fine. Yeah.
You just kind of said that in a lot of the information.
Yeah. By all means, explore that and explore whether there are any issues in relation to curtain wall glazing or curtain wall glazing systems for that. But what you are going to have to do is have a look at the requirements for that building as it's set out in specification C1.1, and then work out, okay, these, so with if we're building on the boundary, these are our FRLs, and then if you're going to be using a cladding system like a curtain wall glazing system that doesn't, or if that system did not provide any fire resistance at all, then you have to say, okay, well this curtain wall glazing system, it has all these features, has all these benefits, it doesn't provide fire resistance in this particular fashion. Then that's that's a consideration for the application of that. It's like, okay, can we apply that to this building in whatever context it's in? Because that curtain wall glazing, that may not be on a boundary, it may not be within 3 metres of a boundary, you may have no issues there. But yeah, for the information that you find on that in regards to fire resistance, put that in.
There's a car park surrounding it, so sure of it. Yeah. There's car parks surrounding the walls. So.
Yeah. So in terms, So in terms of our fire source feature in the car park,
I'm guessing we have to work off this plan to talk about.
Well, you have, so that building gives you an idea of what type of building that we're dealing with. Certainly you can be quite literal in that, and you can go to that depth of analysis and say, look, yes, because we have our car park and our car park is within that 3 metres of the building, that's going to be an issue. But if we're going to have 3 or 4 metres clear in front of that building, and then the car parking happening there, well then we don't actually have a fire source feature, and an FRL is not going to be an important consideration for what we're doing with that, with any external treatments on that building. I don't think we're given any dimensions on that.
No, there is. What, on the car park?
Yeah, let's have a look.
No, but cars normally.
Okay, so those car parks are right there. So yeah, so we're talking 1200 mil off the.
It's also on the site plan.
What's that? Yeah. So it's also on the site plan. Yeah.
So it's 15 metres.
Yeah, 15 metres from boundary, and yeah. So okay, so we've got we've got an idea of, okay, that's our building in context, and if you want to use that context and say, okay, well, we are those sort of distances from boundaries, if we want to ensure that we if we want to be flexible with the materials that we use, we can ensure that we don't have any fire source features around that, and we can use whatever we want. But this report and this subject, it's about exploring those options. So exploring the applications of those materials. So understanding that for certain different buildings, you have different requirements for these things, and that certain different building materials and products can be used in certain situations. And if you wish to make commentary on that and say, okay, we're set away from the boundary, that gives us flexibility in what we choose. We have car parks adjacent. If we were to have those car parks further away, that gives us greater flexibility in what we can use. Well, we don't have to have any FRLs then in that sense. It's just about fire separation between sole occupancy units. Yeah, you can give that advice to your client or to your architect or to your building designer if you wish to go to that degree of detail. If you don't wish to go to that degree of detail, that's fine, because it's about the analysis of these things for a commercial building, and it's not. So let's say we choose a particular type of a cladding system, like something that's, I'll try to think something that's, so let's say we explore the idea of having a timber facade that doesn't meet FRLs. We might be able to use it in one situation and might not be able to use it in another situation. This research is about finding out the information on that particular system, so we can go, okay, we can't use it on this one today, but on another project we can, and you're arming yourself with that information to make decisions about things in the future and researching those things. So is that?
That clears it up.
Yeah. What's that?
Just backtracking a bit. Just have to redo a few things.
Right. Well, so what do you have to redo in that regard?
Well, I might get rid of the timber truss walling inside.
Well, no, you don't have to. Because for fire separation walls, no. So you can use timber stud walls for fire separation walls, and so this is not about the design of this particular building. It's about providing information for making decisions about that building. So you can say, okay, I want to research this particular thing, and we make some recommendations on that. But this isn't us actually specifying those products. This is well before that. So you've been thinking about timber stud separation walls inside. Now you can talk about that, and they may not be applicable, right? But even if they're not applicable, you still discuss them in the report, and so you shouldn't have to redo any of the work that you've done. You've already done that work to say these are the properties that they have, and these are the things we need to consider. But having said that, you can still make fire separation walls from timber studs. You can still retrofit a timber stud wall to make it a fire separation wall as well. So look, I don't know what's behind this plasterboard here, but I could strip it off and find out, and I could probably go to the CSR Red Book. I can't guarantee it, but once I determine what that substrate is, what that framing system is, I go, okay, this is the framing system we have in the Red Book, for example, and that's just one of the design guides. They say if we're using this particular stud system, we have to provide this insulation and this layering of fire check plasterboard to give us that FRL. So you can take pretty much any wall and produce a fire separation wall out of that by utilising some of those components. So timber stud walls, most definitely you can use fire separation walls if they're treated correctly. But yeah, the report is about analysing stuff, thinking about solutions, applications, limitations, putting that information into a report. That's what it's about. So it's not about specifying. So you won't have to redo anything you've done. I don't think.
Sometimes the manufacturer for the product provides those details for the FRS.
Yes, some do. So to do the testing is very expensive, and so companies are only going to plough that expense in if they're going to get a return from selling that product. So, but that's why they do it. They go, okay, we're going to do this research and we're going to develop these systems that pass those fire tests, so that people will start specifying our products, and we'll give specifiers all the information to make it really easy for them to do that. So, yeah, so I mentioned CSR before, like the Red Book. They put out that massive, and it's a massive publication. They do that, and it's got lots of details. And if you go on their website, you can grab all these CAD details or Revit details to be using. They want to make it as easy as possible for you to specify their products for a walling system. And that's why some people produce all that stuff for you, and then others don't, because others go, okay, well, we're not going to be making the money to pay for this. Those guys have pretty much got that locked down. Let's go for this particular market. So
there's those sheets of Danville I was talking about.
Okay.
That go 30, 40 metres.
Yeah. But they've got some purlins underneath them. So we've got the join in the Danville on there where you have your little T-piece there. And so it's so supported quite regularly. But I guess they'd probably be. I just wonder where the end joins are. They wouldn't have been bringing 30 or 40 metre sheets to site, would they? So these grey ones are the Danville sheets. Oh no, these are the Danville. The white ones are Interesting. Yeah. I wonder. Yeah, because you wouldn't want to have a join anywhere on that radius, would you? You want that. In fact, and even that has a slight radius to it. You wouldn't want to have a join.
Because there's a fair amount of wind.
Yeah, I don't know. Yeah, be interesting to see how they got them to site.
It's pretty big.
Yeah.
They use quite a lot of heavy cranes through that.
Yeah. Right. That's all good. So you're pretty much done.
I wouldn't say that.
No, you're not. You wouldn't say that.
Half to 2/3 of the way.
Okay. Yeah.
All the standards are there. It's
pulling it together. Yep. Excellent. And so the energy analysis, that bit shouldn't take all that long to do. You've probably done part of it tonight.
Yeah, I'll do it tomorrow.
Yeah.
Time to relax.
Yeah. Cool. All right. Can I provide anyone else with a bit of assistance in regards to that?